Good evening. My name is Wei Chuen, and today I will present my research titled Enhancing Supply Chain Resilience, a predictive machine learning framework for lead time and delay classification. This research focuses on how we can use the machine learning to predict the shipping delay before they happen, so that factory using the just-in-time manufacturing can protect their production line. So let me begin by explaining why this problem is important. So every day, factory impedance depends on material arriving on time. If one shipment is late, even by one day, the production schedule can be disrupted. Today, the most company only know if a shipment is late or on time. This is the binary answer, so it tell you that what happened, but it is not how bad it is or how long the delay will last. The research proposed a smarter approach. I built a system that took take two types of data, internal shipping record and the external economy signal, and feed them into the machine learning pipeline. The output is not just a leg on time. The output is the potential, the number of the delay day. This gives a logistic manager the information they need to act before a disruption hit the factory flow. Before we go into the solution, let us understand the problem clearly. Currently, supply chain analytics systems have the major weakness. First, the matrix misalignment. Most systems only classify the shipment as late or on time, but this tells us that nothing about the duration of the delay. And a 1 day delay and 10 day delay are both called late, but they have the very different the business impact. Second, the external context deficits. Most systems only look at the internal ERP system. They are completely blind to the outside event. So like material shortages or inflation in the semiconductor market. By the time this should appear in the delivery log, it is already too late to read. Third, data exclusive bias. To keep the system simple, company often remove real or the low volume component from the analysis, but in Penang electronic the sector, many critical parts are low volume, highly specialized. Remove them mean those parts are never monitored, which is a serious risk. These three gaps are the reason why reactive analysis are not enough. To address these three gaps, I designed a 5-step methodology based on the CRISP-DM, the research framework. Step 1, integrated the two types of the data, internal data called transaction record and the external freight semiconductor, the price index data. Second, I benchmark the supervised the machine learning models, random forex, the Guardian boosting, and the Adderbox to find the best one of the for the predicting the delay duration. Then step three, I apply the manual encoding to handle the large number of the part category. This is a smart technique that keep all the data, including the real component, without the making the system too slow. The step 4, I use a sharp interpretability to understand which factor to drive the delay the most. So this makes the model explainable, not just a black box. Then the step 5, the final output goes into the Power BI, the early warning system, a dashboard that gives the manager real-time alert and the recommendation. So now let me explain the two important technique choices I make. First, the integration, the timeline. I connect the internal data call record with the freight PPI data using a year-month key. The integration happen at the early stage of the supply chain, the purchasing request stage. Why? Because the earlier I detect a risk signal, the more time we have to spend. Second, binary encoding. In supply chain data, there are the hundred of different product type and part number. A common technique called one-hot encoding. We turn each product into the one column, and that create the thousand of the column, which is very slow to calculate the data. Binary encoding is a different. It compresses all those category using the mathematical binary representation. The key benefit, it keeps a low volume, uh, specialized part in the data, the ones the method most in the Pinnet OSAT and the OEM factor. So next, let me walk you through the machine learning, the pipeline itself. I use an ng feature, specifically temporal data value and the lake PPI value from 1 and 2 months prior. This time lag signal help the model understand how economy changes upstream, eventually the affect the shipment timing downstream. I test the tree model, the random forest, the handle outline well and work well with the day count data. The Guardian boosting to reduce error in the step-by-step sequence. AWS used as our baseline for the comparison. All three models went through the hypermeter tuning using the Harvin Research CV efficiency, the method to find the best model setting. I measure the performance using the four metrics MEA, RMSE, R squared, and MSLE, all designed for the continuous number prediction, not just the binary classification. The results are clear. Random forest is the best performing models. It achieved the mean absolute error or MEA or just 0.98 days. This means that the model prediction is, on average, less than the 1 calendar day away from the actual delay. Garden boosting come in the second with the MEA greater than 1 day, and the boss was the baseline with the MEA greater than 1.1 day. Why this is so method? Because of the for a JIT factory 1 day method. If a logistic manager know 3 or 4 days in advance that if a shipment will arrive the 2 days late, they can adjust the assembly start time, call for the steady stock, or expedite of alternative supplier. This is the operational value for the sharp day, the predicted the precision. So one of the most interesting finding in this research come from the sharp, the interpretability analysis. I use the sharp to open the blind blocks and see which factor in the models relies on the most. The result was surprising and important. The direct logistic factor like shipping mode and the day of the week order is placed have very high influence on the model output. This makes sense. Choosing air flight or versus a sea shipment immediately change the transit time. On the other hand, the fake semiconductor PPI, the macroeconomic price index, show that the low immediate influence. This doesn't mean that the PPI is not useful. It means that the price shock in the semiconductor market do not immediately affect the shipment. They take time. I estimate 3 to 4 months before the effect reach the delivery level. This is an important finding for the future research. Lake macro signal properly engineered could significantly improve the model accuracy. This research deliver value on the two levels. Academically, it's proved that the three things: one, shifting from the binary classification to continuous regression give the more useful, actionable prediction. Second, the binary encoding is a valid the technique to preserve the long tail and specialize on the data in the LVHV manufacturing environment. The third one, the third one is the macroeconomic signal are relevant, but only when the integrated with the proper time-lapse engineering. So industry, the output for the pipeline the fit directly into the Power BI, the early the warning system. Logistic manager at the Pinnet OSAT and OEM facility can use a what if the simulation slided to the model different risk scenario. When the system detect a potential delay, it automatically trigger a warning. For example, buffer steady stop by 3 days. This finding the gap, this bridge the gap between the economy and research and the factory flow decision making. To close, let me summarize. Supply chain decisions are not the random, they have the signal. The problem is that traditional systems are designed to read, not to predict. This research shows that they are combining the internal logistic data with the external economic signal. And using a random forest regression model with the binary the encoding, I can predict the shipping delay duration with less than 1 day of error. First, looking ahead, there are the 3 areas for the future improvement. First, the hybrid the architecture, combining the graph neural the network with the reinforcement learning for even smarter adaptive decision. Second, the unstructured data integration, using the real-time global news feed to the detect the black swan event the historical ERP data cannot capture. Then the third is an advanced temporal lake engineering, building a 3 to 6 month PPI lake feature to capture the delay effect of the upstream the price volatility. As this research conclude, the transitioning from the reactive tracking to a predictive analytic is not longer a luxury. It is the new baseline for the surviving in the global supply chain. Thank you.